Hello again. Here's something kind of new today. We're going to talk about exact equations. Exact equations I find to be a lot of fun, and I like the steps involved. And once you've done a couple of them, the steps come to you naturally. So what we want to do here is to be able to recognize a particular kind of equation. That's a theme in differential equations, isn't it? And so I want to talk today about equations that look like a function of x, y, and let's just call this one m. So this is a function of x and y, plus another function of x and y that we'll call n. And suppose that we've got a dy dx over there on n equal to 0. So this is a differential equation. It's got the dy dx on it. It's not necessarily linear, but if we can put the equation in that form, it might be an exact equation. Now here's what would make it an exact equation. Let's just suppose that somewhere there is a function f of x, y, and remember y is a function of x. So f is a function of x and y is a function of x. So suppose there is such a function, f of x, y, that has these properties. The partial of f of x, y with respect to x is equal to m of x, y, and the partial of f x, y with respect to y is equal to n of x, y. Now this is m of xy and n of xy from right up here. It's this m and n of xy. Well, what does that tell us? That tells me that the original differential equation is exactly the derivative of f of x, y with respect to x. Now let's check that out. And we have to use the chain rule to do this. But the derivative of f of x, y, the derivative of f of x, y with respect to x, and I suspect this might be calculus 3 where you learn to do things like this. This would be the partial of f of x, y with respect to x plus the partial of f of x, y with respect to y times the derivative of y with respect to x. There's the chain rule kicking in. But under the assumptions, let's suppose there is a function f of x, y somewhere, and it has this property. The partial of f with respect to x is m, so the partial of f with respect to x, this would be m of x, y, plus, and it also has the property, the partial of f with respect to y is n. This is the partial of f with respect to y, so this is n of x, y, and then dy dx. So the differential equation is exactly the derivative of f, and hence these are called exact equations. Now none of that tells you how to find f, or even if f exists, and it may not exist, but there's a simple test to see if f is going to exist. And we'll just write down here test for does f x y exist. And the test is if the partial of m x y with respect to y is equal to the partial of n x y with respect to x, then the equation is exact. And if it's exact, you're going to be able to solve it for f with the techniques that we're going to explore right now. So let's try to remember all of that we've got written down there. Let's try to remember it all, and I'll remind you of things that I think you might forget. So we're going to do an example. And our example function is going to be 6. I'm going to change color for the example. Got all these beautiful colors, and why don't I use them? I really like color. I'm a color enthusiast. So that'll be a nice color. 6 xy minus y cubed, and I'm writing this in differential form, plus 4y plus 3x squared minus 3x y squared, and to save confusion I'll put in parentheses and set that equal to 0. Now this is this the form we started talking about earlier today? Well, yes it is. It's just written in differential form. I had written it as this piece, which would be m of xy, plus this piece, which would be n of xy, dy dx equals 0. But you see, if I put the dx over here, then I've just written that equation in differential form. And you see the equation in differential form maybe even more than you see it as a derivative. So this is the form we're going to use. Now, let's identify things as we go here. Let's remind ourselves that this is m of x, y, and this piece is n of x, y. So our first task is going to be to see if this is exact. So, got to get a color here. So our first question is this an exact equation? Well, to judge if it's exact or not, we're going to look at the partial of m with respect to y. Now I'm abbreviating. You know, this is m of xy. Well, no sense in skimping. So this would be, well, here's m, so let's take the partial of m with respect to y. So I've got a 6x, and the derivative of y would be 1, minus 3y squared. And the partial of n with respect to x would be, now here's n, so taking the derivative with respect to x, that's a 0, and this would be a 6x, that would be 6x, and this would be 3y squared, and it's negative 3y squared. So compare these two. Yeah, it's exact. So if it is exact, if it's an exact equation, we know that there is a function f of x, y, such that the partial of f x, y with respect to x is equal to m of x, y. And therefore, if I would integrate with respect to x, on the left I would get f of x, y, and on the right I would get the integral m of x, y dx, and then plus a function of y alone. Now think about this. I know what m is, right? Because it's expressed explicitly in my equation, so I know m. But how did I get m? Well, I took the partial of f with respect to x, or at least m I know is equal to the partial of f with respect to x. But you think about f being a function here of x and y, and when I differentiate with respect to x, any y terms alone are going to be 0. If it's just y alone, or y squared, or 7y squared, or the sine of y, those terms are going to be 0. And so if I integrate, I'll get f equals m, the integral of m, and some function of y alone. And so I've just indicated that by g of y. Well, let's proceed here and see if this takes us down the rabbit hole, or if we get something interesting here. So f of x, y would be, this would be the integral. What is m? Come up here. You see m is 6xy minus y cubed, and we're differentiating with respect to x. So this would be, I guess, so I don't forget, I can add the g of y. I've got to remember I've got a g of y there. So this would be differentiating with respect to x. This would be 6y x squared over 2 minus y squared. No, it'd be cubed, wouldn't it? Y cubed x plus g of y. And any arbitrary constant could be absorbed into this g function. So we've got, at this point, f of x, y is equal to, this would be 3 x squared y minus x y cubed plus g of y. Now let's scroll up a little bit. Okay. Now I want to just double check because I don't want to make a mistake for you here. 3x minus x, yeah, okay, well, we're doing perfect. Now, so we would be done if we knew what this g of y function was. Well, we don't know what it is. But we do know something else. We know that n of x, y is the partial of f of x, y with respect to y. So that would be equal to the partial of, well, here's f, and so I'm going to put some brackets here. 3x squared y minus x y cubed plus g of y, like that. So n, now what was n? Well, we'll have to scroll back up and remind ourselves of what n is. N is 4y plus 3x squared minus 3xy squared. So n Let's write it down here. Of course, I've forgotten what it is already, but it's 4y plus 3x squared minus 3x y squared, that's n, and that's equal to this partial derivative. So let's go ahead and take this partial derivative. And so I'm differentiating with respect to y. So this is a 3x squared, minus, I'm differentiating with respect to y. So this is a 3x y squared. And now this is a function of of y alone. G is a function of y alone. And so when I differentiate with respect to y, I've got g prime y. So this is a differential equation. Now we can clean that up just a little bit. So let's see what we've got that we can clean up here. Here's a 3x squared on the left and a 3x squared on the right. And here's a negative 3xy squared, negative 3xy squared. And so those will strike out. So boy, now this thing's got pretty simple. Now this thing looks like g prime, I'll put the y in here for us, g prime of y is equal to, now that's all that's on this side, and all that's over here is 4y. And that implies, doesn't it, if I take the derivative, if I integrate with respect to y, I've got, therefore, g is equal to 4y squared over 2 plus an arbitrary constant, which is equal to 2y squared plus a constant. Well, goodness gracious, now we know what g is, and see, we knew f up to g. Now we've discovered what g is using n and the relationship between n and f. And so finally I can write f of x, y is equal to 3x squared y minus x y cubed plus, now I know what g is. G is 2y squared plus c. So there is the f, and the original differential equation was exactly the derivative of f with respect to x. So we've solved the original differential equation, and we should be congratulated. So you need practice on these. I've posted the assignment on Eraser on the homework page, but if you would rather catch it right here, it's page 73, problems 32, 35, 37, and 39. And those are all exact equations, and I don't think there's any of them that are too difficult. But that'll give you practice. And the upload page is already also for these, and it's due a week from today, which is February the about February the 12th. But you'll see it on the Eraser page. So that's all for right now. Thank you for your kind attention.